你需要我 proof 吗？没有。是 Primo 吗？没有，我是说那个 Teams。
你说刚才那一张？
那个是，就是那个 Teams 上面的那个。
等一下，你说刚才那个file还是现在？你在里面吗
I'm not sure。啊，哪一个？
这个 meeting 里面。
我在。
你在？
哦。Lalisa and Sophie are waiting in the room.
Hello, hi Lin, hi Saki.
用你的。
Can you hear me?
Hello, Lisa.
Hello.
I hear you, but hi Lin, there is some echo.
Try again.
有的，Sophie 用我的那个。
I have no idea. 现在在用。
I mean，用我的 speaker，因为我可以那个做 recording。你把你的 speaker 关掉。
I'm close my mic. I'm close my mic already.
Your voice?
Again?
Hello, Lalita.
Oh, hi. Now I hear you.
Hello.
Yeah. Hello.
Just use my speaker. Okay. Lalita, can you hear us?
Yes, yeah.
Okay, great.
Can you hear me? Okay.
Yes, great.
How's how are you? Yeah, it's good. Good. Break is always good.
Okay. So, Lalita, I think for Harry is not in this meeting, so for better review of him, so I will record this knowledge sharing session, transfer session. Okay.
Okay, yeah. Okay.
Okay, it's already started.
Is I'm not sure. Okay, but I can't see it. That's why I don't know if it is started
Yeah, no
recording.
worries, it's already started. So
Okay.
first of all, I want ask for your clarification that for Primo project, is there any additional code uh, um, that involve Massimo module, or because I just discussed with Sogi, she said all codes she's using is just from Massimo module. So I'm a bit confused about this.
So the Mesmo is open source.
Yeah.
So the DRO part is not under Mesmo. It is only for Prima project. So Saki, you remember when you cloned from the GitHub, the Mesmo GitHub, you don't get DRO from it. And the data from it. So those are not open source. All the Primo data, you will not find it online.
The DRO script was inside the Maximum GitHub. It's just the data we provide ourselves.
Right. Yeah. Because the DRO paper is also like a publication, so that's why it's online. But for the data to run those for Primo, those are not open source. So that is from us. Apart from that, there is some work on yeah, the Power Factory Python code, so that is separate, which is not linked to Mesmo. And there is one scripting part that was done for battery sizing, which was done by Rudy from SIT. So that is also not linked to Mesmo. So these two parts are not linked to Mesmo. Yeah, but all the rest. It is using the Mesmo platform.
Okay, so Larissa, I'm not sure if all the codes are included in the Teams channel you shared with me before,
Mm,
right?
um,
It's already
yeah,
included
okay.
in
Yeah, it's included, but yeah, we will do a final update also because we are making some modification with Soki and with the Team Create people. So we will upload it again towards the end of Primo project. But for now, you have the version of it. I think all the part is there
Okay,
on
so
the. Mhm.
everything is in the team is in the Teams channel. There's nothing from like GitLab or GitHub, right?
No, no, no,
Okay,
no.
okay,
Because in the middle it stopped working and it was too complicated to add people from outside. All the code we have backup on Teams.
okay. So what you are doing is to finalize the code and maybe debugging or revise the codes, and you are still updating the codes in Teams channel, right?
Yes,
Mm,
yes, yeah.
okay,
Mainly
great.
because to run with our data set. So our data set is also being updated. And with that, so for our to have our results using this code, there's still some revision going on. Yeah. So that's why we upload a final version later, maybe with the results.
Okay, great. So, how we can do this knowledge transfer?
Okay. Maybe
I just
um
install Python.
mm, okay.
So, um, maybe
Maybe can you enable sharing for me? Maybe we can introduce Mesmo a bit. Then with Soki, we will show you each file in the data set, what it has and all that.
okay. So I will download the Mesmo
I think you have to share, allow to share. I can't
now.
share.
Yeah, I think I cannot share now. It's disabled.
Lalita,
Mm,
you can share screen
okay.
now. Yeah,
Yeah.
because I just change your role into a presenter.
Okay. Yeah. Okay. So yes, you can see my screen, right? So this Mesmo is the open source one. It's actually a platform by MIT, and Tum Create is working on this platform also. So it's just open source. Uh, yeah, so you will find and a short introduction here. So if you go to GitHub, Mesmo, dev Mesmo, um, so it's basically a power system modeling where you can do like a simulation, like run load flow to find the losses for DC network, for AC network, for single phase, for multi phase, and you can do optimization also for the grid. But the additional interesting part is it can do the same for like a thermal grid model. So we can have like a separate electric grid model, and we can have a separate thermal modeling also. Like thermal grid meaning like you have a cooling plant, it is supplying different buildings for cooling load, or or even heating load you can model. So the building, in this case, the building cooling load model will be built by defining all the surfaces in the building. What is the characteristic of that surface? What is the area of the building? So all the building parameters that is coming from the architecture drawings. So you need to input those for getting this cooling load model. And for the cooling plant, depending on what the plant facilities are there on the campus, so you get the data from that. So that will be the thermal grid modeling.
Okay.
And mm,
I have a question here. For the model, for the load flow calculation in this model, is it stochastic modeling or deterministic
Uh,
modeling?
it's the inbuilt one is just deterministic. So
Okay.
DRO is the only part. DRO is the distributed robust optimization. That is the only part which where you can model uncertainties. So this part was done specifically for this Primo. This part. So it is not like fully developed. So far, it can model only price uncertainties. But later, if you want to add some uncertainty or probability distribution for renewables or load or something like that, then you will have to build on it. It is not already there. All these basic ones are fully deterministic, except that one robust optimization.
So inside this Massimo, there's a robust optimization and the
Mm.
distributional robust optimization, right?
Yeah, there is a stochastic optimization and there is a distributional robust optimization.
Ah, okay, okay.
Two different types of optimization to model and to do optimization with uncertainty.
Yeah, okay.
Mm,
So for this part, last Friday we had discussion with OSLIs.
mm,
They are trying to they asked us to provide a model, mathematical model of Primo, so that they can test their some toolbox, mathematical toolbox,
mm,
based on our use case, based on our data. And Edward is trying to push forward this collaboration um, uh, between SG office and France Auxiliaries department.
okay.
So what I'm going to do now is to write down the mathematical model, the constraints and the objective functions, constraints and objective functions, etc. So I'm not sure if you have this kind of materials or everything is in journal papers.
Um, yeah, the formulation would be from the journal papers only. Apart from
It's
that, we
very
don't
difficult.
have. Yeah, yeah, yeah. Apart from that, so when you share with Osiris, so they want the data or they want the formulation.
They want
So what?
mathematical formulation.
Oh, okay, okay.
Yeah,
But what is uh, the use of sharing that? That means this mathematical formulation is for DRO, right? So if they
yeah,
want to do something else, so they want to use it as an example.
yeah. The things that last Friday I told them now we have some difficulty of solving DRO optimization problem because the computational complexities really high.
Mm,
It's not easy
yeah.
to solve the problem. So
Mm, mm,
they share with us that they have some decomposition algorithms to decompose large scale optimization into small piece of optimization problem, and maybe this kind of decomposition can help to reduce the computational time. So
okay. Mm,
actually, the toolbox actually tries to improve the computational efficiency for large scale normalization problems.
Okay, okay. Mm-hmm.
So
Um,
yeah,
yeah,
that's
but
why they
it
require
is
me
true.
to write down the
Um,
mathematical formulation.
Oh, okay, okay, okay. We try. I mean, you can also pass the code to them to try with our data. It is true that it takes forever to solve, but the problem with Primo is we don't have any uncertainty data. We have only deterministic data. We have all the information we need. But for uncertainty, we just try it by giving some fake uncertainty values.
Yeah, yeah,
We
yeah.
don't have
I
any
also,
data behind
yeah,
it.
no worries,
Mm.
no worries. I also told them we assume some uncertainty
Yeah.
on our PV generation data and demand data. That's no problem.
Mm.
They're just concerned about the mathematical formulation.
Okay.
Yeah,
Okay.
because
Okay.
the intention here is to test their decomposition algorithms. Mm.
Okay, okay, okay. The reason you don't find like very detailed formulation is because we are like building on this Mesmo platform. So things like power flow, those constraints, they are already sort of there in this platform, and we are just building on top of it by defining what objective we want to minimize. Then we just it's like I'll show you in the code. It's quite easy to add power balance constraints like that. That's why you don't find more detailed formulation, I think, because it's built on top of this platform.
Oh,
Yeah.
and Lata,
Mhm.
would you mind pausing a bit? I want to take my pen and the notebook here. I can write down your answer.
Okay, okay, okay. Yeah.
Okay, so the reason why we can see all the details here is that everything is included automatically in
Yes,
Maximal.
it's only the extra things that we need that we would need to code. It is it's like, so if you look at the DRO code, for example, so this is the DRO part. Mm, Let me show you an example. Um, so here, like, um, if you want to define some constraint or something, it's it's
I thought I
okay.
couldn't see.
Oh,
You
yeah, yeah,
couldn't
yeah.
see,
Okay,
yeah,
okay.
couldn't see.
I'm not sharing the screen. Okay, okay. Sorry.
Yeah, but I think it's still showing the screen.
Um,
You know.
Okay.
Okay. So for example, so this is from the DRO code, right? So, for example, they want to add some power balance constraint. It's quite, you don't have to code everything from the matrices and everything. It just uses the Mesmo template to add the constraint. So that's why you won't find very detailed model. You just use this electric grid model to add the constraint. So it's quite, it just has to use the same kind of template to add. Automatically from the template, it will take all the DERs from the data that we give in DER model. We will show you the data set. So it automatically takes the data from that, and it's so um, like using that platform, you can easily add the power balance constraints or any other constraints. So that's why it's not fully mathematically formulated in the papers. Is just a general formulation is given, because if you want, for example, to write a new script, you just have to like copy this. That is just it. This platform does it automatically by taking from the data set in the CSV, the different DERs, the DER models, and then depending on the name that you give, you have to do it in the same template, and then it automatically adds this constraint. That's why you won't find very very detailed things in the paper. In the paper, what useful thing you can find is what they want to minimize or optimize, that you can find. So the objective function will be quite detailed. So this part will
And
be.
hey, Lalita, I want to ask you for the uncertainty, right?
Mm.
Uncertainties come from PV and electricity price and demand, or just for, or it just comes from electricity price.
Only from price we have taken here.
How do you? Okay, so the uncertainty data, the uncertainty of price, these kind of
Mm.
things are already included in the
Um,
electricity price data in.
no, no, no. Let me show you an example. So, so now we went straight to the most complicated DRO, but there is so much before it. So for example, maybe I'll just uh, let's leave DRO a bit for later.
Okay,
Maybe
okay,
just
sure.
the basic part I will tell you. Then the DRO has additional data like this uncertainty data. Okay, so once you clone the GitHub, you must see this. I'll Okay, maybe. So how to include the data? So it's in this folder. So you will have from the examples, you will have some IEEE 4 node, 34 node, 123 node. So all these are example which you will get from by just cloning that Mesmo folder. Now this is the one that we added locally with Soki for SIT and GTC, that is for Primo campus. What are all the data? So inside this, you give your full data folder. Maybe I let Soki share the screen. She has the latest ones. Then we can go through it.
Okay.
Soki, can you share the screen for showing the files?
Yeah, sure. I put it in different place, but it's the same. So this is
Okay.
the one that I'm using right now.
Yeah, so in this, so this is like the standard way to define if you have a new system. So you give all your data also in the same template. So here, the first folder, COBMO data. This COBMO is this control-oriented building model. That is all the thermal part. So inside that, you will have these different files that define like the different building thermal models. So it could be cooling or heating, which you model. So for those, the data has to be defined in this way. So this one, it was done also for Primo. They from the building architecture. So you like, can you open one by one? Okay, sorry. Mm, so this has to be defined for like each building. You need to have the thermal data. So the building name. So you see all the buildings in SIT JTC. So we have taken some for the all the missing data. We have taken um, this cooling plant type, for example, plant heating type. So all these were not clearly defined in our data. We couldn't get more data on the campus. So we have used like some information that was inbuilt, like from the library of the MESMO. So the CEA plant cooling and all is like different types of cooling defined in MESMO. So we use it, and maybe the next file. So for each type, so under each building, for example, W1, W3, those that you saw in the previous file, those are different buildings. And each building will have different types of rooms, like lecture theater, like food court or auditorium, like that. So for each type of those, we build a thermal model and integrate them in one physical building. So for those, we give some constraints. So temperature, maximum, minimum, and airflow, maximum and minimum. So these are the only parameters, but you could also define if you want to go for a more complicated model with more details, then you could define like humidity. You can define more constraints, basically. In our case, mm,
So for the time range, is it 24 hours day 1 day optimization or 8,700 hours in
you
time
can
zero
optimize
optimization?
how much you want. You can
Okay.
optimize how much you want. But here, how it is given, it's on weekday, 24 hours, you have constraints, and weekend, 24 hours, you have constraints. If you simulate like 1 month, then it will just repeat.
Okay.
Weekdays, it will continue to use that data. And on the sixth day, it will change the data.
Okay.
Saturday and Sunday, it will
Okay.
change the data. So it is like a repetitive schedule. If you give only 1 day, every day will be the same day. If you want to change it, then you can give another day. It will just
So
repeat.
the data pattern between weekdays and weekends are different.
Ah, yes, yeah. Due to the occupancy, needs for cooling are different, right? So constraints are different. So here it's only two constraints: temperature and airflow. Yeah. So maybe next one. So like this, I also don't know all the details of the thermal part, but I try to share what I know. Um, can you expand a bit, Saki? The heading. Um, yeah, this is like the how to say, like the cooling plant, the heating, ventilation, and cooling all together. We need to give some set point for initializing. So this is like the initializing for that. And like you can give the efficiency. Here it's just ideal case, so one. But if you know the losses of the cooling plant, you can give it. Um, yeah, and there's also like just like the engine type, there is also a heat recovery system. So it's treated like the generator of the thermal grid. So this is that one.
Mm.
And
Yeah, sure.
okay, maybe not all. Then I think we'll take a lot of time. Maybe scenarios. Okay. So for scenarios, you initialize. So that is so here you see the starting time and end time. So depending on how much you want to simulate, you can change. And this one actually you can change it in one file also. Then it will automatically get reflected in this file. I will show you that one, or it's up to you. You can change in this. This location is given because if you want to run, for example, just the thermal grid, you don't want to run the electrical part, then you need to define your start and end and the time step here. If you are using the electrical grid, then there is only one scenario file where you can change. It will automatically get reflected here. Then the surfaces, I think you can close it. Yeah.
Scenarios. Um,
Normally, the scenarios is the general file where you give the settings to run the start time step, end time step. If you want to run different scenarios, like give like different parameters, different initialization, and run multiple scenarios, then you can list them in the scenarios file. Then you can choose which scenario you want to run. So scenario is like the general file that you change. It's like the config file.
okay. Mm.
Mm. So in surfaces files, you will have like like I mentioned, right? For each building, how the thermal model is built is by defining all the walls, the roof, floor, and the type of the wall and the area. So, like for W1, what all it comprises of, that is the zone name, library, auditorium, whatever, whatever. Those are in the zone name, and for each zone, we define constraints separately in a in previous file. And we need to give like the direction of I mean the wall, which direction it's facing, and what is the surface area of that wall and the surface type. So here we use only one surface type, wall, green mark, non-residential. So if you just input that, it will automatically take from the library the parameters of that non-residential building wall. So we just use the inbuilt information from library.
Okay.
If you have those information in your system, then you can create a new surface type and define it separately. So,
Okay. Okay.
like a custom type. Mm, okay.
I'm curious about how who defined this file and how this can
Um,
be defined.
it's coming from the, so what we did, we talked to SIT JTC to get their architecture drawings.
Mm.
So from the drawings, remember previously I was showing you the 3D modeling.
Yeah. 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 Yeah.
Yeah, so from that you get the surface area of the walls and all that. So that is the surface area you see here. And each building, we ask them how much of area is occupied by lecture hall, by these different types. So we gave them like 10 types of areas in a university, and we ask them to fill out each building has how much percentage of that area occupied. So with that information, we got this one. And because we don't know all the information about every wall, what material, how much thickness, those we don't know, so we just use the non-residential uh, type from the library, which was already there in Mesmo.
I remember you're using uh, a software or something that is from from the initial project. in the off.
Yeah, yeah, right. Yeah,
Okay.
it's from that one that we get the surface area. So in that software, you can input the 3D, the architecture drawings from the architect. Then we automatically it computes with you have to align it to the GPS um, in that location, and it automatically measures the surface area.
Okay. Sure.
Okay. Yeah, so you can um yeah, you can close it. Okay. So the next one maybe just zone type. So zone type is this each type of area like auditorium, classroom, for food and beverage, hostel, so on. So we classify each of that, and we give um, and we give like what you call the. Can you move to the right? We take from library um, this type of heating ventilation, what do you call that, heating ventilation air conditioning, so HVAC type. So we just take it from the library, this one, the information for different types of zones.
Mm.
Um, yeah, I think, yeah, so it's just integrating all the data that we got, and what was for the missing information, we use some examples from the library to build up. So that is all. This COBMO data is for all the thermal related data. Then coming, yeah. Next is, yeah, maybe scenarios. So this is all the electric grid part. So that folder is all the thermal, and from now it's all the electric. So the scenarios file is like the main file. It's like the config file where you make some settings to run. So here you give a scenario name. You can give multiple scenario names. You can have multiple scenarios. You can either use electric grid, thermal grid alone, or use both. So you define that there. Then the parameter set, if we want, we can give a parameter set. You can give a file called parameter set, which will like make the config settings like that. You can prepare a file and give. If you don't have, also it's okay. It can be empty. Um, Price type. So here in from the library, we have a few price files. So Singapore wholesale is one of the price data that we have in the library. You can call the price file there. If you want to use your own price file, then you can create a price file in the same template and give that name over here. Yeah, we have Primo price, right?
Yeah.
Maybe that you can show. Yeah. So it's just the price type, you write the name here, and the time every half an hour, every 1 hour, it's up to you. You give the price and the value. Value is in dollar per megawatt hour. Yeah, and this price type name, you need to give it in the scenario file. Yeah, that name you give it over there. So this one is using a different one from library. So we give this name. Price sensitivity coefficient. This one, like, so it's doing the optimization, right? So you can define like some sensitivity. If yeah, for you it doesn't matter like few dollars, then you could give a different price sensitivity. For
Mm.
us, we just give 0 for now. Um, then the next one, what is it? Electric grid operation limit. Oh yeah, you can like give operation limits like voltage limit, line flow limit. You can give those parameters and name that file over there. Similarly, for thermal grade, also you can give some operation limit, capacity operation limit, and give it that. Then time start to end, it could be 1 day, 1 year, it depends. And interval for us, for now, we do 1 hour. So far, we are running 1 day very quick. 1 month also is for deterministic, it's not at all a problem. But when we go for to stochastic or to DRO, I think even 1 day it takes forever to run. It depends what DERs we have. If we have only the load and PV, maybe it's fast. If we include some thermal part, it is like very slow.
In fact,
Yeah.
it doesn't make sense to me.
Mm.
As far as I understand from from stochastic optimization, even if you generate scenarios, I mean, uh, uh, given a particular level of uncertainty for renewable generation, you can leverage on this uncertainty to generate a lot of scenarios. So uh, even in that case, we utilize some scenario reduction or like scenario tree or things, such kind of things to reduce the number of scenarios. So I'm not sure in Mathmo or in this Python code any reduction, any scenario reduction techniques is used.
No, I
Okay,
don't think so. No.
that's why.
Yeah, yeah, that's why it depends on the time we are simulating, um, and it depends on the number of DERs we have and all that. If we include like too many flexible loads, then it is like very, very slow. Um, yeah, I don't think any reduction technique is used.
Okay. No wonder.
Okay. Yeah, so the time is defined there. And for the base power, base voltage, yeah, so far we use that. And ours is 22 kV high voltage, 400 volt low voltage. That is our system for Primo. So we use 22 kV. Then the next one, base thermal power. If you're using like a full thermal grid, then you define base thermal power. Then the tra- yeah, sorry, go ahead, Saki.
Uh, for this, actually, this one is optional if we look at the data reference. There's not.
Okay, yeah, yeah, good point. Yeah, we can also show maybe the data reference to him. It's much easier. You will have it in your folder, no?
I'm not sure.
You don't want to.
This
Yeah, I think
this
it's there in your folder.
which
Yeah, so this is like the file where you can get the information, what it means, each column, what it means, how you have to define. So all the data, what template it should be, that information is in this one. I think maybe go back to your folder. I think you will find it.
for I
Um,
think it's in library.
Data, uh, not in library, just in data. Oh,
Data
you don't have?
for you mean the
Wait. Maybe just come just in Mesmo.
just now the maximum? Yeah,
No, and the folder Mesmo. I mean.
I'm not sure.
Yeah, I think, wait, docs. Yeah, should be there. Yeah, you will find data reference, installation guide, publication information. Yeah, you will have all the documents here. So data reference is will give mm, the information what it means each CSV what it means.
Okay.
Mm. Okay. And some are like optional, like Soki was telling. We don't need to define everything. Some things you can also leave it blank. So that information you will get in the data reference. Okay. Okay, I think this is complete. Then the next one, I think electric grids. Yeah,
Yes.
yeah, yeah. So in electric grid, you give the name of the electric grid, which we also have to use in the scenario file, and the source node and frequency. For due to like since it's running for a long time, um, we use like single phase equivalent. But if we have three phase data, then we could use three phase. So and then so like the electric grid lines, nodes, those ones you will be able to define all the grid. So in ours, we have four feeders. These feeders are connecting um, from the main grid to the campus grid. So those are the incoming feeders. So we take node 0 as the grid, and from node 1, it's the campus. So N0 to N1, and we only take a single phase equivalent, so only one phase will be enabled. Mm, yeah, no nodes maybe. Mhm. Yeah, so the nodes and ours is 22 kV, the HV nodes, and 430 for the low voltage. The latitude, longitude, if we want to give it, we can give it, but it has no significance in the optimization so far. It's good if you want to create some plot later, depending like a drawing of the grid or something, then it will do it with the latitude, longitude. But so far in our code, it doesn't use it. We don't give it. Okay.
Okay, so
Mm,
for grid nodes,
mm.
how come there's a M5.1, M5.2, and 5.3?
I think it's just a name. It's because like the N5, I think is plot 2, right, Soki?
Yeah, this point one
Uh,
is part two.
okay. N5, the whole node is all the buildings connected to one plot 2 of SIT. So she named it N5, and different buildings inside that plot, like 5.1, 5.2, but it is just a name.
Okay.
Yeah. Then maybe so you can define transformers. Line type, we give matrices, also impedance matrix. So that is line type matrices. So in this, we have two type of cables, I think. Yeah, this campus, we had like two types of cables. For those cables, we got the data of um, resistance, reactance, capacitance. So since it is single phase equivalent, we just define 1 cross 1 matrix. If it is three phase, we need to give like 3 by 3 matrix. Um, okay, maybe the operation limit type. So this is where you define the voltage limit and the branch flow limit. So in your optimization, you want to add voltage constraint, branch flow constraint. Yeah, we need to input it here. But the problem is so far you can't set different constraints for different branches.
Okay.
If you give it here, it will just set 95% as the constraint for all the lines.
Okay. Okay. Sure.
If you, okay, yeah, can maybe next DRs, electric grid DRs. Okay, so this is the more interesting part. Okay, so okay. So for the DERs, it could, so this is the file to list all the DERs that we will be adding to the grid, electric grid. So here, even though it's called DERs, we need to define all the loads, all the generators, everything only in this file. So under DER type, so the fixed load means is just a load where we give data as time series. So every 1 hour, like we give the setting, or every half an hour, we keep the setting. So that is fixed load. Then, so here for us, it's all the buildings. We have the fixed load, and we separate the load as cooling and non-cooling. Um, we separated because later we want to include the cooling part under the thermal model. So that's why for us it's like that. And then you have fixed EV charger. Fixed, oh, where is it? Oh, yeah. Fixed EV charger for SIT for two different zones, two different plots. We have two combined and fixed generator. In our case, it is the PV because we are not curtailing the PV. It's just fixed. So we input like a time series pattern to this. So it's treated like a fixed generator. Um, Waste to energy, that is the W2E, that we give it as flexible generator, means we give the maximum for every hour. We tell this is the maximum we can produce, and then it's up to the optimization to control it. So we just define the maximum. um, then the next is the battery. We give the type as storage, and then we, for the battery, we can give the settings also, the capacity and everything. So that I'll show you separately. This is just like this, the file to list out everything and to tell which node each DER is connected and what type it is. That much only. So then after that, you have flexible building now. Okay, yeah. Flexible building is the thermal cooling model that we developed for each building. That Cobmo model we showed at first. So that part is this one. So flexible building, it will integrate the Cobmo model in the electric grid. So this is flexible building, and flex EV charger, you can make it fixed or flexible. If it is flexible, then in the optimization, it will automatically control. So that you can give it here. And last one is also fixed load. And in the last column, the 0 and 1, you can enable or disable them. So if you want to run like different scenarios, you can give the enable disable accordingly and try to rerun it. That's what we are doing with Socky now. So to try to run different scenarios where we have certain DERs, we don't have like we have battery, we don't have battery, then what is the difference? Are we making any money out of the battery? So to understand like that, so we run different scenarios. So for that, we you can enable or disable in that in service column to check. Um, Yeah, then you can give reactive power. In our case, we don't have that data, so we just give the nominal active power. But the nominal doesn't mean much here because more detailed model are defined. This is just like initializing part.
Okay, okay.
Okay. Um, then so now we just listed it here. More details are defined in the DER models, that file. Okay. So, okay. So fixed load, um, for fixed load, we need to define like a time series. So in the definition type in column C, you just have to give schedule. Then that means it will follow the schedule that we are defining. So it's just the type. For fixed generator, for that is PV in our case, for that also there is a schedule. So just list as definition type as schedule. Then, yeah, for battery, for example. So for battery, mm, okay, it's hard to read. Okay, so for battery, we can't define a schedule, so it has to be controlled. But you can define other parameters. Um, yeah, you can like give the energy storage capacity, for example, power maximum, minimum, P max, P min. Then you can give energy storage capacity, charging efficiency, self discharge rate. Yeah, these are all parameters for the battery that we have to define. So in our case, we just input um, some efficiency, self discharge rate, I think, and the capacity. That's all. Um, yeah, but if you have more details, you can model that also. Then for flexible generator, even though it is flexible, we give like a schedule. Um, uh,
External meeting.
are
Later
you
when
there?
Harry needs the meeting room, so
Oh, okay, okay, okay. Oh, hi, Henry.
so we have to translate to other place. The
Okay, okay, sure, sure. Go ahead.
okay. Okay, we come back.
Okay.
Enjoying it.
Yeah. Okay. I was just kicked out.
I think we can go on.
Yeah, we can carry on. Alisa?
Yes, yeah, yeah.
Yeah,
Okay. I was just um okay. So for waste to energy, so it's a flexible generator, but we still have to give like a schedule, because we will give so like for example, like the in our case, for the waste to energy we have like operating hours. So the optimization will be able to control it only in those operating hours, and in that operating hours we will define the maximum we can generate. So the optimization will be able to control and dispatch it accordingly. So the schedule will define like the maximum we can generate each hour. So that is the flexible generator. Then for fixed EV charger, we also need to give schedule of charging schedule. So that part I think we can show you. Yeah, we have multiple schedules, I think, so it's better to show you later. Then for flexible EV, you also have like multiple schedules. That part, EV part separately, we will show you the file. Then fixed load, as usual, it's just schedule, it's time series. Okay, so now we wrote all the schedule here. We will need to define the schedule, right? So that is the next file, DER schedules. So first file where we list the DERs, that is electric grid DERs. Then the model of each DER, that is DER models. Then some of the DER models will need like a time series input. So that one is in DER schedules. So here we give the definition name. So this definition name will be included in the model file, DER models file, and we will give like every hourly time series or half hour time series. It's up to you. But so here the time period 01 T so on so on. It 01 means the first day. If you want to define weekday and weekend, you can give 01, then 06, 07, you can give. If you want just the same day every day, for example, like PV, you don't have weekday, weekend, its generation profile is the same. So you will just have 01, T 0001, so on. So this is for the fixed load, you have weekday, weekend. For PV, you must have normally only weekday because every day is same typical profile, right? So you will just have 01. For some, you could even have like only few hours. Then after those few hours, it will repeat itself. You can also have it like that. You just have to set the data in that way. Okay, so maybe waste to energy. Can you go to that? Yeah, so here, so we just give in the operating hours. So from 8 a.m. to like 7 p.m., we give the maximum capacity of the generator. So the optimization will, in that time, it can dispatch differently. The schedule. Um, yeah, I think the remaining are also loads. So yeah, pretty much the same. Okay. Okay, so that is for DER schedules. Then just for EV, we didn't define still. So that is under DER EV charges. Okay. So so for EV, we need like multiple data. So for flexible EV, we will need maximum charging, then maximum discharging profile we need to give, and maximum energy profile, I think. Then the last one is the when the vehicles are leaving, so you have the departing profile, departing energy profile, then nominal profile.
What is departing energy profile?
um Depending on the data of exiting vehicles. So like if you have a schedule of the vehicles leaving at that particular time, then it has to follow it as a constraint, right? While doing the charging. So that's why we give this definition. So it's maximum charging, maximum discharging, um, maximum energy, and departing energy.
Yeah, and for this one, there's no any uncertainty of EV charging
Um,
profile.
yeah,
Everything
yeah.
is known.
Yeah, here this is fully deterministic, but I mean, it would be interesting to model, but in our case, it's just a time series,
Yeah,
no uncertainty.
I mean, in most of cases, the departing time and arriving time of the EV
Mm, mm-mm.
has
Can be,
can be
yeah,
uncertain.
mm-mm.
Yeah.
Yes, yeah.
So in some some people will use the prediction algorithms or some deep learning AI things to predict the arriving time and the departing time of EV, and this is how the EV uncertainty come from. I think okay,
Mm,
I think this model just simplify the simplify the EV scenarios.
EV modeling, yes,
EV
yes, yeah,
model.
yeah.
Okay, understand,
Mm.
understand. Okay,
Yeah,
so
and the last one, nominal, it's for fixed EV. So nominal will only be used when you give like a fixed EV charging, then it will use the nominal charging profile. If you give flexible, then it will use the maximum energy, maximum departing, and all that as constraints to do the control.
mm, okay, okay, sure.
Okay, then this should also be in the schedules, no, Saki?
We put it in
The definition of this one.
it's like also the schedule, but it's
Ah,
just
okay,
for
okay.
other.
But in a separate folder.
Mm.
Okay. Yeah, so you should have like fixed charging. Is that the fixed charging profile? So this one, if you see like it's given for like the full week, you will have the data for all the 7 days. Then after that, it will repeat itself. So, and maximum charging, maximum discharge, then maximum energy, I think maximum energy that you can store, then maximum departing, oh no, departing energy is
Maximum departing energy. Okay. What is
depart
departing energy?
departing energy is like uh, uh, sum of all the battery storage that is leaving, sum of all the EV battery storage that is leaving.
Okay, 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 okay.
Yeah, and the maximum energy is the sum of all the energy storage capacity of EVs at different point of time.
Okay.
So, arrival of vehicle will kind of be accounted in maximum energy. Um, is it okay?
Okay, okay.
Okay. And maximum charging, maximum discharging, they are power profile, power maximum Pmax and Pmin. So that is maximum charging, discharging. Maximum energy is the maximum energy storage capacity of all the vehicles that are parked. So it will somehow account the arriving vehicles also, arriving vehicle data also. And for departing, we give like a departing energy where at this hour so many vehicles leave, so so much storage is leaving. So
Mm.
yeah, so with those series, and for fixed charging, I think the first one is the fixed charging profile. If you scroll to the top, I think the first one, Yeah, so if we give fixed EV, then it should normally we use this profile. Okay, so that is all the DERs that we used. So mainly fixed load. Then we have a battery. We have a fixed generator PV where we define like the PV time series. Then we have a flexible generator waste to energy where we input only the maximum generation in the operating hours. Then we have EV fixed and flexible. Then we have all that thermal model in the flexible building. So this is uh, so this one what we show just now is only the SIT part. For JTC, it is the same DERs only,
Okay.
but with a different capacity, different system.
Mm.
But it's the same. Um, yeah. So yeah, maybe we can try to run. Maybe Saki. There are different ways you can run it. You can run nominal operation, which is just simulation for power flow. It's possible to run that.
Sorry, Laita. Wait. Um, so we just download Massimo code from GitHub, which is free.
Mm.
And what kind of what kind of data we should put into this project?
That is all the folder that we showed just now.
We just showed
So
this now, so
mm,
data. It's just data set. We need to include this data set
yeah,
into Python project, right?
yes, yeah, right.
Okay. There's nothing. There's no code anymore. Okay.
You can use the already built code.
Already what?
Yeah,
already inside.
Uh,
which is already in Mesmo. So the basic code you can
what?
run.
So okay. So for now, you are trying. You are doing the you are doing the optimization over a new version of DRO, right? Not it's not the original. It's not the original Python code. It's not original DRO Python code.
We are modifying it.
Oh, okay.
Yeah. Um, okay. So even apart from DRO, so DRO is just for stochastic. Um, but just if you want to run just deterministic, you can just run. Maybe can you go back to the folders, okay? Um, yeah. So far we input the data in the data folder, and so this is where you need to input the data, and yeah. So okay. So in examples, when you go to examples, you can use run API nominal operation problem if you just want to run like a simulation, like you're just running like a load flow. Then you can use nominal operation. If you want to run just optimal operation with the data set, then you can just use the next one, run API optimal operation. So this is like purely deterministic, but this is like inbuilt in Mesmo, so you can't control much what it is doing and all that. You can't change the objective, for example. So objective is the cost in this case. So it will minimize the total cost of electricity. But how it is computing that and everything, it just uses all the data and constraints that you set in the data. It will use the price time series. It will use the DER model. For thermal, we set constraints in the DER model itself. For battery, we set some constraints. For EV, we set some constraints. So it will just take the constraints from the data. It will say take the price data that you define, and it will simulate and optimize for that interval that you give. So this is completely inbuilt. You can't control it, but so this is the simplest that you can run. So normally, if you give data in the correct format, you will already be able to run these two. So maybe first we can try run that. So here in the scenario name, you need to give the scenario name that you give in the data. So even though you give like data as different folders and everything, finally it will all be written into one database. And in that database, it will just link to your scenario name that you're giving.
Okay.
So you just so can you show where the scenario name is in the data? In the data, this folder in the scenarios file, we give a scenario name. So this scenario name will define your entire data set.
Mm,
So you just copy that scenario name on in the script, then it will locate all the data constraints associated with that.
mm.
Okay. Then we just put the update the name and run.
Well, where's the result?
Oh yeah, yeah. We're just okay. Maybe after she runs, she will show.
Occasionally, I used to use VS Code instead of Python. I don't really like Python settings.
It's the
Simple
same
settings.
thing, I think. Yeah.
Huh?
It's just the editor, right? It
Yeah, it's just
doesn't
the editor.
matter.
Yeah, but
Mm-mm.
sometimes, one time I realized the definition. Oh, is really okay. I'm really sensitive to red things. Red means red flag or arrows.
Okay.
Line is the one that tells the result is stored already.
Ah,
Yeah,
okay.
so it will
Can
display
we
the
go?
location.
Okay. Can we go to the folder that is store the result?
Results in
Ah, okay.
that will come out this.
So you can imagine how much Saki ran. She has so many folders in results.
Okay.
These are all the results.
Ah, this result can be your FYP. This is already your FYP project.
Yeah, yeah, she has a lot to write on the report.
Ah, okay, great. Okay, great. Yeah, yeah. This is what they call applied learning. Yeah. Normally, I feel like in NTU, everything is theoretical and not pretty much concrete programming or or hands-on skills. So I
Mm.
think this, yeah, so this FYP project is really valuable and promising. It's really helping
Yeah,
me.
can you imagine she's only in her second year now, no, Soki?
Oh,
I'm now
She
the
in third
first
year.
of third year.
Third
ah,
year. Mm. It's not even her FYP. So she's just going to start her FYP. So imagine her FYP.
so what will be your, what kind of topic will be your FYP project?
I'm not sure yet.
So SIT FYP project will be attached in the industry or it's just do something
They
in
should have
university labs.
they should have settled different projects. But if you since we are doing internship first, if like we can collaborate together with your the internship company to
I
do
think the
a
continue.
right I'm not sure.
No, this is just continue. I think because
Yeah, yeah. I told her
we
also,
support you.
like,
Yeah,
just
we
do
will
it.
support you too.
Hmm.
So
So what will be that? What will be the project that is doing for that?
yeah, I think EDF Labs Singapore office will be very supportive. You can continue your work here.
Mm.
Okay,
Okay.
okay. So
Okay. Maybe we run the optimal.
oh, okay. By the way, let's recap. What is the difference between optimal and normal?
Nominal is just the simulation. It will just run PowerFlow for all the initial settings that you have given. No optimization at all. So no cost, no. no price, nothing. So it's just the electric grid and thermal grid, everything together. It will just simulate and initialize if you want
Okay.
to see the nominal output. But optimal, it will optimize the cost, total electricity cost.
Oh, okay. So normally, we will use uh, optimal thing, right?
Yes, yeah, yeah. Nominal, I think, is just good to check the data if we made some error or something.
Okay.
I think I'm running nominal right now. That's why they only like give this like result of
Mm,
data. So there's no like objective value.
Ah, okay.
So if I run in nominal optimal, let me see.
yeah.
Then it'll tell you the objective values and then
Okay.
print it inside the results. So this is the two
What
found.
is inside? What is inside?
Inside this two found,
Yeah.
one of them is just the log of this or of this.
Okay. Estimation results.
The rest, the another one is just the Excel file for each different, like which one you want to find out.
Okay.
Like you will get all the settings of DERs for yeah, and the grid line data, I mean line flow and all that.
Okay.
Okay. So this is like just deterministic basic one. Um, and then maybe can we run DRO stage one? So under DRO, so can you show where to find DRO in the folder? Okay. So you go to Mesmo, example, publications, and this 2021, you will find uh, the scripts and a data also attached to it. So in the script, you have main, stage one, stage two. Stage one is the deterministic part. So it's possible to run only the deterministic also in DRO. And this is more
Sorry.
controllable.
Stage one is deterministic.
Yeah, deterministic.
Huh?
But the difference between this deterministic and what we just run before is that this one will optimize energy and reserve. It is a co-optimization of energy and reserve, which is not the case in the
Reserve is
one we run.
okay. A reserve is provided by.
It could be provided by battery or the generator, the flexible generator. Yeah.
Okay. So okay.
Yeah, and stage one, I mean, don't go with the name. It is just an indication. Like stage one is the basic, it's deterministic. Stage two is the like the stochastic part. It will use the stage one to run deterministic.
Hey, if I'm
Is
not
it a
wrong,
bit clear?
okay. If I'm not
Okay,
wrong,
not
I
yet.
think the
Mm.
first. Okay, if I'm not wrong, I think the in robust optimization, two stages are optimized simultaneously.
Ah, yes, that is true. So here, stage one is like a function
Okay.
that will run deterministic. And if you want to run DRO fully, including all uncertainties and everything, you have to run the DRO underscore main. So that will call stage one function, stage two function, and the different things. And stage one, if you want just the deterministic part for energy and reserve, then you just run stage one. It should give the deterministic. If you want to include the full DRO, then run only DRO underscore main.
Okay, okay.
Okay, and that is the DRO part, and SO main, that is stochastic optimization. So that is just one script if you want to run stochastic optimization. And all the uncertainty data. So far the data has no uncertainty. All the data that we show you, it's just deterministic data. So you can run DRO stage one with just that data. If
Wait, wait,
mm,
wait. For DRO, I think, okay, for DRO, the uncertainty is from electricity price, and
yeah,
what percentage deviation you assumed in this data?
so
This,
can you open DRO underscore data, that folder? Okay. Yeah. So here, so how uncertainty is modeled, it is given in different time series. So it has max, min, and variance. So it uses like this variance and the mean
oh, okay, okay. So
to
can I
model.
say,
Mm.
okay, so can I say, for the electricity price time series, it has for each time instant, it has max, mean, and max maximum value, minimum value, and mean value,
Yeah,
right?
yeah, right. Yeah.
The mean value will be the predicted value.
Mm.
Okay,
And then
okay.
you have, yeah. So this data is specific, but it is not real data. It's just what is made up to run that. Doesn't mean anything. So
Okay. It's a presumed data.
yeah, presume data to test it. And if you go to price forecast, basically. So in this one, we need to input the normal price and the reserve prices for this one. So even though everything is listed here, the optimization will use the, in this case, the USEP, Uniform Singapore Energy Price. So it uses that one for energy pricing. And for reserve pricing, it uses contingency. It doesn't use yeah, only these two we have modeled fully in our thing. So for example, battery can contribute to contingency reserve. We have only taken that. We haven't defined like two types of reserves, primary contingency. We didn't do that. It's only one reserve and energy trading. So these two are combined. So for price data, you need to give these two.
Okay.
Mm,
So, I mean, for each dispatch period,
mm.
how do you know this? How do you know this generator will be called to provide contingency service?
That will be like the result of the um, optimization.
No, I mean, um,
So depending on like for example, when the contingency price is very high, um, it the optimization will co-optimize energy and reserve. So the battery in that hour it can be dedicated to reserve depending on the price. So it will maximize the revenue. Is it okay?
I mean, mm,
So the objective is like it is the total revenue coming from the reserves minus the total cost of electricity.
okay.
So this one you optimize, and by taking into account the reserve price, it will automatically co-optimize this one.
Wait.
Then
Uh,
mm,
but I thought you have regulation price and primary price.
Yeah, yeah.
Regulation
But
price. This is reserve. No.
um, but like regulation is more like it has to be more active, right? So we have not modeled all that. Regulation, it depends on frequency and all that. So that part we haven't modeled. That's why we just go for contingency reserve. Means every half an hour we know whether we are participating or not. So it's just that it doesn't depend on frequency in this case.
Okay.
So to simplify
So
it, we use contingency reserve. But actually, if you want to include also co-optimize along with like regulation, primary contingency, then it means that depending on grid frequency, it will be involved in the optimization. So um, that part, yeah, we did not do that.
uh, okay. Regulation primary service. Regulation is frequency regulation, right?
Yes, yeah.
And we don't involve any frequency regulation service here,
No,
right?
in this optimization, no.
Okay, and for primary, secondary, uh, I think this is
Also,
what is this is a what's this? This is a primary frequency. Am I right?
primary is it also depends on frequency, right? So we have not modeled that also.
For
Contingency, it doesn't depend on frequency. It's just like the grid operator calling us to um, for the reserve. So we only model that one.
yeah, yeah. I mean,
Mm.
you write down regulation and primary. I think the primary and regulation here refers to the same thing. Both of them are frequency,
Uh,
primary
oh no
frequency.
no no! Actually, this table is exactly what you can get from the EMC website. So they display all this, and we have just taken that data directly to
Okay.
yeah. I think yeah, Saki has it that price information. Yeah, so you see, so it's directly from this EMC website what we took, and there you have different categories like regulation, primary, secondary contingency.
Oh, okay.
So regulation, in my understanding, it depends on it's the automatic generation control. It is AGC that one, and primary, it I think you have to activate in very fast um,
Okay.
and for contingency, they give 10 minutes for you to activate. So we just take and you see the price for primary is very less compared to contingency. Because primary, you have to last only 10 minutes, I think. You have to be on for like 10 minutes. Um, and so it's hard to model that. For contingency, you have to be on for half an hour. Means one dispatch period fully you have to be on. So it's easy to model that. So we just took the contingency, and the
Okay. So
price is also high. So
yeah.
uh,
So how do you utilize the contingency price? I'm not sure.
if
What does this contingency
mm,
price is used for? Is used in the optimization model?
okay, so maybe Saki, can you go to DRO stage one, the script which you just opened? Yeah. Okay. Can you go to the objective? To know where it is? Yeah. Just below, just below. Define objective. Okay. So here you see, yeah, this part. So you have um, a price time series energy and price time series reserve, right? Um, so the energy price time series energy, that is the uniform Singapore energy price, and price time series underscore reserve, we have taken the contingency
Okay.
price.
Okay.
And yeah, so so
But
it's just
for here
mm,
we don't model this reserve. reserve is for in this reserve the reserve here means contingency.
Yeah, means only contingency.
Ah,
Yeah.
okay.
Mm.
Um, hey, where's the price? Okay. Ah, the price. Okay.
So in this, we have like two types of reserves, up reserve and down reserve. So up reserve meaning we must like when called, we must increase the generation or decrease the load, is the up reserve. Down reserve is the opposite. We must increase the load on call. Right now, that is not there in Singapore. There is only up reserve in Singapore. But just, I mean, we also model down reserve,
Okay.
imagining some future scenarios.
Okay.
But so
Wait.
far, there's
And
no
yeah,
down.
and and this is objective function in first stage. So I assume
Mm.
that in stage two there's another objective function which involves a lot
Involving
of scenarios
uncertainty.
or huh?
Involving uncertainty. Yeah, yeah, you're right.
Yeah, okay. And so yeah, for you have this objective function in the first stage, and I think in the second stage you have to actually preserve some capability, preserve some energy for preparing for this contingency call, right?
Yes, yes, yeah, you're right.
Initial reserve call. And how much reserve you have to. That depends on how
Um,
you model it.
how much reserve means that will be the result of the optimization. At what hour, how much we dedicate for reserve, that is like the result of the optimization. That is the this what is that? Decision variable.
Okay.
Maybe we just do one run and show you the result, maybe more clear. So here also you must update the scenario name, right?
Wait. Um, the variable is what is decision variable here?
Decision
No,
variable is all
reserved
the
bid, reserved bid, decision variable. I mean, yeah, just in this page.
yes, the up
The
reserve and
decision.
down reserve.
Okay. So the first one is up reserve. Up reserve times its price. Then the third part is the down reserve time its price, right? Okay, decision variable. And I guess this reserve will be somehow included in the second stage.
Um,
Do you remember?
so the second stage is including the uncertainty. But what all? But you're asking about um, keep maintaining some capacity for the reserve. Is it?
Yes. Because in the second stage, so what
No,
is
no, no. All that part is covered only in the stage one because if, like this is because it will still be deterministic, right? What you're asking. Um,
can we see the constraint in the first stage?
Above, I think
Above
about this. I think can you scroll up?
constraints.
Yeah, power balance.
Where's the power balance? Okay, power balance here. And up reserve is this one?
It's like it's three scenarios. Um, Up without any reserve, when there is up reserve, and when there is down reserve. Three scenarios you
Three
will see.
scenar three scenarios. Define constraints.
That's why maybe if you run and see the result once, I think if you see the plot, I think it will be more clear for you.
So Elalitha, what does upper reserve constraint look like? I I can't see clearly here. What what does constraint look like?
Um, so up reserve meaning like when you are called, you must be able to increase the generation
Too great.
power. Yeah, so it means like the battery discharging power, for example. So, or it could be a reduction in the load. So, we have a lot of flexible loads. It could be a reduction in the load or to increase the battery discharge. So battery has some power constraints, and flexible building also we have already defined the DER constraints. So those two together will define how much maximum up reserve we can provide at that time.
Yes, yes. I mean, so for the intraday real-time operation,
Mm.
um, uh, yeah, the up reserve is 24 times. Sorry, upper reserve in stage one is a 24 times one vector, right? Each hour we have a up reserve and a down reserve. So what I mean is that this reserve capability are determined by day ahead, and for the second day, the reserve for each hour cannot be changed. The,
It has to be rerun.
it has to be what?
It has to be rerun after
Rerun.
any modification. Like if you're asking if something changes, like if some reserve got activated or it didn't get activated, then what happens to the next time, right?
Yeah. Not normally. Okay. Can you agree that the up reserve and down reserve are determined a day ahead?
Yes, yes, yeah.
Oh, okay, determine day ahead because
Mm,
we use this profile. We
mm,
submit this profile to beat
mm. Yes, yeah,
to
exactly, yeah. Mm,
EMC or something.
yes, yeah.
You tell them, oh, tomorrow I will I will keep part of my capability standing for your emergency call,
Yes, yeah.
including up reserve and the down reserve, right?
Mm,
So
mm.
for the intraday, the second day, you have to you have to be really careful about in your real time operation. You have to be really careful not to use use out your energy in the system. You have to preserve this capability according to the day ahead agreement with people.
Yes, yes, right, right, yeah.
So am
So
I
you, as part of the result, you will get the DER, each DER's power set point also. So that will, in a way, to ensure that you will have reserve for that hour. If you're running one day, optimization, you are getting from the result of optimization the optimal bidding that you can make. You are
Mm.
getting that which hour you want to participate as reserve or not, how much energy you're buying each hour. You get that as the result, and along with that you also get the DER set points as a
DR
result.
set point.
The set point of each flexible generator, the set point of the battery also you get.
Okay, so in the first stage, decision variables
Ah, yeah.
include up down up reserve down reserve exchange with the utility,
Mm.
right? And
And
set
the
point.
DER set points.
Okay, and DR set point. DR here means battery.
Yeah, any flexible controllable. So here it's waste to energy, battery, and building load that you can control.
Okay, so yeah, you have a set point of each DR,
Mm.
and in the
For three
second
scenarios, for three scenarios,
for
you
first.
get it for a no reserve scenario. You're not activated, then you just follow that. You get a set point when you're activated for up reserve. You get a different set point. Um,
You,
and for down reserve you get a different set points depending on whether you're activated or not. You can correct it in real time.
okay, okay, or scenarios here.
That's why you take a look at the result, then maybe more clear for you.
Okay, okay. Um, okay, I think it's a little bit different from um what I defined previously for DCAS project. So I'm curious about this. Yeah, maybe I can run this code later on, and I can ask you if I have any further
Yeah,
question.
maybe just now we can run it. This part, at least the deterministic is quite fast. So it will give you, I think, from the
Lolita,
plots you
is there
can
any okay?
understand.
Lolita, is there any interaction between first stage and the second stage? I do think that there are some links between the two stages.
Um,
I mean,
by stages, you mean the scripts here,
uh,
the
I, I
scripts
mean,
in
I
the
mean
code.
modeling.
Oh, okay,
Yeah,
okay.
I
In the
think
modeling, there is link here. When we say DRO stage underscore one, that script, it is a function, and DRO stage underscore two, there is also a function, and inside that you call stage one, which is deterministic. Mm,
inside the stage two, you have to call stage one.
yes, yes, yeah. And inside stage one, it's independent. It is just deterministic. That's why you're able to run it separately.
Okay. Wow, it's a magic kind of magic.
No, no, no. I think the Mesmo just makes everything simple. If you look at the script, I- you will see you really if you want to include any constraint, it's very easy to write. I think the Mesmo platform just makes it very simple.
Yeah, yeah, okay, yeah, understand. Um, why you can write down um, optimization constraints in that easy way is that we prepare all the data beforehand,
Yeah.
right?
Yes. Yeah.
And we have to ensure the data is prepared correctly. So that's
Mm,
why that's why the Python code here is much easier than.
yeah. Yeah, then in the platform, if you give it in that template under this name, it automatically has a way to integrate those constraints already. So if you just put power balance constraints and you put a certain vector name, it's already what to say, like it's already built in that platform.
Okay.
Mhm. So this one, you see, this is the
Okay.
deterministic.
Okay, so Lalita,
result.
you mentioned that in the first stage we consider three scenarios.
Yeah, yeah,
Yeah,
right.
and for each scenario, we run a deterministic optimization, or we combine three scenarios together and run a deterministic optimization. Sogi is already
It's
very tired.
independent. It is it's independent. So if you open power balance, so maybe one by one, power balance. So this is the results you're seeing of stage one, deterministic. So you see, so here there is three independent runs. So no reserve stage one, that is separate. So if you're just participating in energy bidding, you just go with the blue bidding bid curve. And for up reserve, you go with for just up reserve, that is the orange one. For just the down, it is zero now because we don't have any price for that. So there is no down reserve in Singapore market, so it's just zero. But if you have that, you can model it. And the other reason is also no, no, no. It's just because there we did not input any price information for that, so it's zero. And no reserve plus up reserve, it means you're doing energy bidding and up reserve bidding. That is the red one, and the blue is just no reserve minus down reserve. That is the same as blue because the down reserve is zero.
Yeah,
So
I
it's
I I
independent. It's
I think
independent
yeah,
scenarios.
I think for each times for each dispatch period
Mm.
um there's it's possible for you to be called or and it's also possible for you to not be called, right?
Yeah, yeah,
So
exactly.
how
Yeah.
is there any modeling of this possibility? No,
Um,
I don't think you.
no, but we need to ensure that in both cases we are able to act. Um, that is what we included. You see what I mean? So if we are activated and if we are not activated, it should still meet all the DER constraints
Yeah,
and all the grid constraints. So we will do two scenarios. And for in those two scenarios, we must still be able to meet all the constraints. So that is how it is modeled. So can you go to like 1D or Soki, maybe the battery or something like that, or flexible building, anything,
long results.
anything, just open anything. It's okay. So here you'll see there is a optimal value in no reserve stage, in the up reserve stage, and in the down reserve stage. So you get like the DER set points in the three independent cases.
Ah,
So so this is like an information to the operator day ahead. This is not real time. Um, we are not taking like it's activated. So now what we modify, that part we did not take into account. But in the feasibility, in the constraints, both the scenarios are modeled. If it is activated, then also we should be able to meet all the system constraints. If we are not activated, then also we should be able to meet all the system constraints. So like in the place of one constraint, you will have two constraints in this optimization. That is the only difference. So for each DER, you will have three independent scenarios like an information to operator beforehand.
however, for battery, uh, for battery, the power of battery at time t is coupled with the SOC of battery SOC at time
Yeah,
t is
yeah,
coupled
right.
with is coupled with the next time step and the previous time step prior time.
Yeah,
So
yeah.
if you just classify,
But that is why you're running both the all the scenarios, right? You're running whether it is activated or not activated. You're running the all the scenarios for like the 1 day period. So um, So it will include all those combinations, what you're saying.
It includes
Do
all,
you see what I mean?
includes all the combinations.
Means whether it's activated or not activated. Then in the second period, when you participate as reserve, whether it's activated or not activated. So it's doing this for the whole period that you're optimizing. In this case, it's a 1 day optimization. In 1 day, if you have 2 periods in which you are participating as reserve, then it will include four constraints. Means you have a situation where you get activated for first one, you don't get activated for second one. um,
Do you
does
have
it make
any,
sense?
yeah, okay. Do you have any uh like explanations, explanation notes or slides when you are when you are developing these codes uh, to show me
um,
any slides?
I think so. I think, yeah, we will have. um,
Maybe just look at the formula will be clearer.
mm, share my screen. Maybe this will be useful. So this is some slides from Kai. But it's
Yeah,
also,
okay,
the
okay. This is
content you
useful.
have.
Yeah, this is
Okay,
useful.
it's the content you have on the paper, but it's just it's shown some comments on this. I can share this with you. Then you have stage one problem. This is, you see, it's the same as the one in the paper, but it's just like with marked with some comments.
Oh yeah, this is useful. Yeah, maybe you just download it and send to me.
Okay. I show you this.
Oh, this is
Then
also, I guess this is also in the Teams channel, right?
maybe not. This one is in our folder with Tum Create. This one, yeah, it's a lot of
Okay,
content
you
to
have
put.
downloaded everything.
Okay, I will show you.
Yeah,
So
otherwise reading John Kai's paper is really a suffering.
complicated.
It's really complicated. Nothing
Okay.
inside. All
And maybe
formulas
this
and all.
slide, maybe this slide is useful for you. So first, whatever simplification he wrote there, that is in the first stage. Then we go to the market clearing
Mhm.
stage. It's kind of the questions that you are asking, right? So I will share these
Yeah.
slides.
maybe yeah,
Okay.
you just download everything. I can go through in very detail to understand what is
Okay.
happening here.
Okay, 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 okay. I will put this folder, copy it, and put it on Teams from here.
Yeah, yeah. Okay, okay,
Okay.
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 It's really hard to explain orally
Uh,
if we don't
uh,
see the formulas here.
yes, yes, yeah, yeah. Um, okay,
I guess
okay,
you are
okay.
very tired now.
Yes, we had another meeting with Saki, but yeah, I told him it's going to be too hard today. Yeah.
Okay, okay. Maybe okay. Lalita, no worries. You just send me the folder you downloaded from Team Creator sharing folder, and
Mm.
I can read up that formulas, understand what is happening there, and if I got any question, I can ask you later on.
Okay, okay,
Sure.
okay, sure. So like, but you got some idea how to run it and all that, right?
Yeah,
Uh,
I roughly got the idea how to run it,
okay,
and yeah, I will try to practice later on. No worries.
okay, okay, okay.
Yeah, thank you so much. Thank you for time.
No problem. Uh, you.
See you. Bye bye.
Bye bye.
Jovi,
Saki,
right?
you want to discuss something? Then we can just do it in the
Yeah.
call.
For now, I don't think there's any
Sagi needs a rest.
Saki needs rest. Yeah.
it's
Yeah, but just for the call with Jian, so he told us to send what is the problem by email, and then maybe tomorrow or the after he will tell us another time to discuss.
yeah.
Today uh, he's not free after 5, so I think we can't talk to him today. But maybe we can write an email to send him.
Okay, yeah.
You prefer I do it?
Uh, but in email, were we able to tell him that directly?
Exactly. It's very complicated to. I don't know what he will understand, but I'll just tell him and ask if we can meet tomorrow afternoon.
Yeah, sure, sure.
Um, Um, do you have the half hour price of 2022 that we need to like edit with him?
You mean
No,
code?
right? I don't think. Yeah. So we want him to prepare this script that will change the half hour file to the 1 hour for this 2022 data. So we need to send him one file, right, to prepare the script for
But
the
like this, that
input.
means I need to edit the price forecast out.
But you don't have it yet, right?
I don't have it yet.